All right, welcome. Today, we are jumping into one of the most important skills any site engineer needs to master, making sure your site control is spot on. This is literally the foundation of your entire project, making sure everything gets built in exactly the right place. So, you've probably seen it, or at least heard the horror stories. You're on site and something just feels off. A building foundation is out by 100 mils. A brand new road doesn't line up with the old one. Or maybe the worst one, water is flowing away from a drain. What's the single thread connecting all these massive, expensive headaches? Well, you know what? 9 times out of 10, it all comes back to the very beginning. It comes back to the control points, those fixed survey pegs that everything on site is measured from. Everyone assumed they were correct, but nobody actually checked. And it's those little unchecked errors at the start that don't just add up, they multiply into huge problems down the line. So in this explainer, we're going to break down exactly how to prevent that. We'll look at what happens when control goes wrong. I'll show you the elegant solution. We'll walk through the work in the field and in the office and really hammer home why this process is absolutely critical. First up, let's really dig into what happens when you don't verify your control. And I'm not talking about theory here. This stuff has very real, very tangible, and believe me, very expensive consequences on live job sites. Check this out, a real-world example from a road project. They ran a check and found a 250 millimeter error. That's a quarter of a meter. Can you imagine if they just started paving based on that? The entire road would have been built in the wrong spot. We're talking catastrophic rework. This is the exact nightmare scenario we're trying to avoid. Okay, so how do we dodge that bullet? How do we give our site a proper health check? We use a classic, incredibly reliable method called the closed traverse. Think of it as the ultimate safety net for your survey control. So what exactly is a closed traverse? The concept is actually super simple. You start at a known, trusted point, you measure your way around a loop of other points, and you absolutely must end up back exactly where you started. It's like walking around a city block. If you end up back at the same corner, you know you've closed the loop. And that simple geometric fact gives us a powerful, built-in mathematical check. Now, this is a really important distinction. An open traverse is like a one-way trip. You measure from A to B to C, but you have no way of knowing if small errors were creeping in along the way. But a closed traverse? That's the round trip. The fact that you have to come back home proves you stayed on course. And that's exactly why it's the gold standard for reliable site control. All right, enough theory. Let's get our boots muddy. How do we actually do this when we're out on site? The process in the field is methodical, almost like a dance. You set up your instrument over your first point, let's call it point A. You take your measurement, your angle and distance to point B. Great. Now you pack up, move everything to point B, and you do the exact same thing to point C. You keep doing this all the way around the loop. And then the grand finale, the most important shot of the day, is from your very last point back to your starting point, A. That's what officially closes the loop. Okay, fieldwork's done. You've got your data. Now you head back to the site office, grab a coffee, and it's time to crunch some numbers. This is the moment of truth, where we find out just how good our survey really was. And we're basically looking for two kinds of error, or what we call misclosure. First, did all our angles add up correctly? We call that the angular misclosure. And second, when we plot it all out, did our loop actually close? That's the linear misclosure. Let's tackle the angles first. You might remember this from school, but for any closed shape with a certain number of sides, all the internal angles have to add up to a very specific number. It's just a fundamental rule of geometry. So we just add up all the angles we actually measured and compare it to that perfect theoretical number. The difference? Boom. That's your angular misclosure. Next up is the linear misclosure, and this one's way easier to picture. Once you've calculated the coordinates all the way around your loop, you check the coordinate of where you ended against the coordinate of where you started. In the real world, there's almost always a tiny gap between the two. That physical distance, that gap, that's your linear misclosure. So let's say you just finished a 400-meter traverse around your site, and you find a gap of 80 millimeters. The first question you have to ask is that good, or is that a problem? And the answer is always, it depends on the job. We calculate the precision as a ratio, the error divided by the total distance. So 80 mils over 400 meters gives us a precision of 1 in 5,000. Now, looking at this table, You can see that for general construction, hey, that's totally fine. But if you're setting out steel columns for a high rise, no way. You'd need to be way more accurate than that. So once we've confirmed our misclosure is acceptable, we're happy with it, but we don't just leave it there. The professional thing to do is to adjust our measurements to completely eliminate that small error and make the loop mathematically perfect. And the go-to method for this is called the Bowditch rule. The best way to think about it is that it takes that tiny closing error and it kind of smears it out fairly across all of your measurements. The logic is simple. A longer measurement probably has more room for error, so it gets a slightly bigger piece of the correction. It's a very logical, fair way to balance the books. And here, you can see the magic in action. Look at the original column. You see how the last point, A, has a northing of 500.045? It missed the start. But then look at the adjusted column. See how every single coordinate has been nudged just a tiny little bit? The result? The final point lands perfectly on 500.000. Now that is a solid, reliable, and trustworthy control network you can build from. So let's zoom out for a second. Why do we go through all this trouble? What's the big deal? Well, it's simple. This whole rigorous process is about turning uncertainty into precision. It's about turning I think this is right into I know this is right. Think about a multi-story building. On one project, this exact process allowed the team to lock their control grid down to a tolerance of just 5 millimeters. That meant zero chance of columns not lining up from one floor to the next. I mean, that's what prevents structural nightmares. And it's not just about things going up. It's also about things flowing down. For drainage, having the correct gradient is everything. A verified control network means your pipes have the right fall, which means you avoid blockages and catastrophic failures years down the track. A hidden but incredibly expensive mistake. Okay, let's boil it all down. What are the key things to remember? 1. Poor site control is a direct line to expensive errors. 2. The closed traverse is your best friend, your #1 health check. 3. You must always check your angular and linear misclosures against the project specs. 4. Use a standard method like the Bowditch rule to adjust your network. And finally, remember that this entire process is about turning doubt into confidence. So I'll leave you with this one final question to ask yourself every single time you step onto a new project. The control points might be in the ground, the coordinates might be on the drawing, but have they been truly verified? The success of your entire project depends on that answer.